I'm going to talk about artificial intelligence, and I would love to be able to talk about the future, but that hasn't happened yet. So what I'll do is mostly talk about how it evolved, how the attempts to make computers act intelligently developed in the early days up to the present, and see if that will give us a flying start to predicting what will happen later. But of course, the future lies ahead, and we can't see exactly where it'll go, but we can make a few speculations. So there are lots of problems that we'll face now and in the future, and we can sort of classify these future problems as ones that are fairly imminent. Here are 4 or 5 of them. There's a danger of serious climate change. What can we do to ameliorate that? And one thing we can do is try to estimate what each kind of climate change we're likely to cause would cost, and start taxing the activities that might lead to that. Politicians will have a big struggle listening to the scientists about that, but many large industries, such as the oil and gas industries, it appears that they'll have to be seriously constrained, and there will be gigantic political quarrels about how to do that. Same thing for health costs and stuff like that. Then there are larger scale disasters. For example, the sun, which is our main source of energy, will become a nova in about 4 billion years. It's used up about half its lifetime already, and someday we'll have to worry about that. But I don't think we need to spend much time on that now. A serious problem that will face us pretty soon, and we'll be happy to face it, is that as we conquer more and more diseases, the lifespan of the average person will increase, and within the next century, maybe we'll live an extra century. This will cause a problem if the population keeps growing, and so the people of the world will have to decide on some way to constrain or even reduce the total population, or else feed them more efficiently. Interesting problems in that realm. If people live to be an average age of 100, and many of them approaching 200, they may not want to work so hard. It would be nice if we could extend lifespan without deterioration, but it seems somewhat unlikely. So we'll need smart robots. And smart robots will need to be able to understand problems as well as workers do today. And today, none of our machines are very smart or perceptive or intelligent. In fact, I've been disappointed that, as we'll see shortly, there hasn't been much progress toward making machines smarter since the 1970s or so, when progress appeared to be very rapid. Anyway, one thing we learned in the early days of modern computers was that if you can't solve a problem one way, then a good thing to do is to have several ways to solve it so that you're less likely to get stuck. And if you look at the human nervous system, you see that humans are very good at that sort of resourcefulness. This slide shows a dozen different ways to recognize objects and to visually estimate where they're located with respect to you. A normal, healthy person has 2 eyes, and they can use focusing and stereo and that sort of visual system to locate objects. But even if you have only one eye with pretty bad vision, there are lots of things you can do, and this slide describes some of them. Aristotle discusses human resourcefulness, and he characterizes our ability is to describe things in multiple ways so that you can switch from one to the other. One person might describe a house as a shelter against weather. Another might describe it as stones, bricks, and timbers. A third person might describe it as something made with those materials for those purposes. And so we have different kinds of descriptions for different purposes, and we don't see things in just one way or another, but a smart person can see anything in several ways and juggle the different meanings. We still have yet to do that with our computer programs, but I expect that that will be the main line of progress of getting computers to seem smarter in the future. This slide shows 8 different ways to make machines solve problems, but don't have time to discuss them all. Between the beginning of computers, which was really the late 1940s, and the next 20 years, there was a great deal of progress in getting computers to solve mathematical problems. Some of the earliest programs, in 1960, one of our students named James Slagle wrote a program that could do integral calculus quite well, and in fact got a good grade on a first-year MIT calculus exam. In the next few years, we had programs that did pretty well in high school algebra and logic and geometry and all sorts of mathematical subjects, until we had programs that could do most of the things that a good math student could do in the early college years. It seemed quite remarkable to make so much progress. Here's James Slagle's, an example of a problem in calculus that James Slagle program solved in 1961. And here's a program that Daniel Bobrow could solve in high school algebra. And here's a program in 1964 that could do 10th grade high school students problems in geometric analogies, which was something that many people thought would be outside the ability of computers. Anyway, it seemed easy in those days to make progress in getting computers to solve highly technical problems, but it seemed almost impossible to get programs to solve the kind of problems that 2, 3, 4, and 5-year-olds could solve. In other words, the common sense things that every normal person can do seemed more difficult to capture in terms of procedures that computers could do than the highly specialized skills that our highly paid experts can do. Every child knows that you can pull something with a string, but you can't push it. Why is that? If you asked a child to explain it, it would be pretty hard. Euler wrote a complicated paper about that and gave the calculations to show when pushing on a thin rod could push another thing or would bend. And that was took a lot of advanced mathematics. So here's an example of an everyday situation. Two children are playing with blocks, and if you ask, what's the little girl thinking? Or here are a dozen, well, 8 different questions that she's already got answers to in some sense. What if I pulled out the bottom block? What would the little boy, what would her brother think? Should I help him with his tower or knock it down? How would he react to those? Where's the long flat block? It was there a minute ago, and so forth. When a child is doing what seem to us as the simplest things, every second of that activity is involving asking new questions and guessing answers to them and doing reasoning processes that to this day no computer has been able to, or no computer programmer has been able to accomplish in one program. Well, how did all this happen? About 6 million years ago, our ancestors, human ancestors, started to diverge from the other primates, and one could ask, what were the changes in the brains of those animals that led to the greater intellectual abilities of humans? That's still a bit of a mystery, because the brain scientists, of whom there are the order of 1 million, know a great deal about individual neurons and a little bit about how neurons are connected to each other, but very little about how the assemblies of brain cells work together. Typically in the cortex of the brain, maybe 300 or 400 cells are arranged in a column, and there are many millions of such columns. We know a little bit about what these columns seem to do, but we know almost nothing about how the results of the calculations in several of these columns interact with those in others, send signals along bundles of millions of fibers to other parts of the brain, process the information then in other ways, send it back and forth, and so forth. So we know a great deal about what happens in individual and small assemblies of brain cells, but almost nothing about what happens on larger scales. So the next 20 years, I hope, will get the neuroscientists to move their scope up to higher levels and start to meet the larger scale theories that are coming down from the artificial intelligence community. I would guess that at the present time, there are several 100,000 neuroscientists working on the low-level problems, and there are perhaps 400 or 500 people in the world working on the higher-level artificial intelligence problems. And so I hope the next decades will increase the number of people working on the higher-level theories. The funding for that was very generous in the early days of 1950s and 60s, because there were people in the Defense Department who thought that artificial intelligence was important. Paradoxically, several liberal senators felt that it wasn't a good thing for the military to be funding such basic research, and ARPA changed its name to DARPA, and the funding for high-level artificial intelligence actually sharply decreased. Most of my students in the 50s to 70s became professors, and almost none of them in the next 30 years because of this shift in public funding, largely. Anyway, it's pretty clear that however the brain works, it's composed of different levels of processing. And it's interesting that in the late 19th century, Sigmund Freud wrote a draft of a paper on a theory of how the brain was organized. And he even went down to the neuronal level. Although very little was known about neurons, Freud had the idea that learning occurred through the strengthening of connections through synapses, and he wrote a big paper that no one would publish until it actually didn't see the light of day till around 1950, when Karl Pribram arranged for Freud's project for a scientific psychology to get published, and that was the first public view of Freud's beautiful early theories. They weren't quite right, but they were 50 years ahead of their time. Anyway, however the mind works, we can think of it as a collection of different resources. If you look at the brain, everyone knows that different areas of the brain seem to do different things. We know very little about how they're done, but we know that here's an area for speech and here's an area for vision, strangely at the back of the head, as far from the eyes as you can get. And here's high-level thinking and so on and so forth. And many different areas of the brain have been identified roughly with different aspects of thought. And however those things work, it suggests that we can think of, it's profitable to think of the brain as lots of different specialists. And so you can make simple theories, and this slide shows a theory of emotions, which suggests that when you're angry, a certain collection of brain centers are active and many others aren't. When you're hungry, another set, and when you're afraid or when you're thirsty, yet other groups of cells are being operated, but they're not all separate. Some of them are common to many different emotional states. And the same thing is probably true of higher level thinking. Like if you have a problem and you're stuck, what should you do? And this diagram suggests 4 things you can do. Can you split the problem into several parts and work on them separately? That's a way to make progress. Can you make an analogy? Can you think of another problem just like that? So in any case, either for emotional things or for intellectual things, each mental state you can think of as activating some particular set of mental resources to various degrees. And each fragment of knowledge might work in some situations and not others. I'll just mention a few early projects that I think are right now buried in the past and could deserve being revived and extended in the next few years. Pat Winston wrote a brilliant thesis, I think in 1972, about thinking as being based on finding differences between things and modifying those differences. So that was an outcome of early cybernetics, a beautiful subject of the 1940s. Another model that grew up in psychoanalysis was the idea that the mind is full of critics, which are watching parts of the brain or parts of the mind are constantly censoring or criticizing or praising and selecting activities, making lists of them or networks of them, and as you proceed from one state of mind to another, you rearrange your resources and get better and better, if you're lucky, at dealing with the kinds of problems you're facing at the moment. I'd like to see much more research aimed at that level. So I guess my hopeful prediction about the future is that there will be a reallocation of resources from the large amount of money and energy that is now being directed toward low-level neurological science. Now, that area is very important because diseases and handicaps of the nervous system are perhaps the most troublesome and disturbing problems of health of all the problems we face. So we don't want to slow down our research in the medical aspects of neurology. However, I think if we're going to try to improve things for the future, we should move some of our resources, more of our resources, into higher level theories of how the minds work and how they can be made more effective and improved. And my prediction for the 2040s is that this will happen more slowly than most of us think, but eventually it will happen.